This video is going to start our conversation around capacitors, which we did cover at the very bitter end of the um, electrostatics, because capacitors still have a little bit of a static or field reference that we're going to be using a lot of. So, quick review from the parallel plates that what we did at the end of um, our electrostatics with um, electric potential across the plates. So, parallel plates, when they're connected to a battery or a voltage source, build up charges on each side. And this causes a large, consistent electric field between the various sides of the parallel plates. And as always, fields store energy. So we can determine that energy by looking at the voltage across the plates, the electric field between them, and the separation, how far apart those plates are. And then use that voltage would be the change in electric potential energy over charge. So if we're looking at parallel plate capacitors, this is literally two plates, like metal plates, that are parallel to each other, okay, and oppositely charged, one positive, one negative, and they're separated by some type of insulating material. We're going to use air for all of our examples. Okay, so what happens if you look from the side? There's a distance d apart. One side is positive while the other side is negative, and there is a giant field going from the positive to the negative. Okay, and if you look at this with an angled view, so instead of looking at it straight on, you look at it at kind of an angle, you can see that there's actually an area there. And this also is here to represent that there's a voltage being applied, or once the charges begin to build up, there is actually an electric potential difference across the two plates. So we just started what the parallel plate capacitors are. And what they do is separate the charges. And their ability to keep these charges separated from each other is a quantity called capacitance, which we represent with a capital C. Now, capacitance is basically defined as the charge on one plate, the positive plate typically is the way we think about it. It's always a magnitude of charge, divided by the voltage across the plates. Okay. Something to keep in mind with this is that it's the ratio that is consistent. And if you change the charge on one of the plates, that's because the voltage changed. You can't change the charge to change the capacitance. If you change the charge, you change the voltage. And so capacitance is going to have units of coulombs per volt, which is known as a farad. Now, if you want to change the physical capacitance of a capacitor, if you want to change the amount of the capacitance, um, you have to change the actual physical makeup. So that ability to separate charge is a constant. Okay. So if we want to change that, we have to build a different capacitor. And capacitance is going to be A over 4 pi k d, or epsilon sub 0 A over d. Now, what does that mean? C is the capacitance. That's the thing that we want to change, or, tells us how well that physical device can separate charges. That's in farads. A is the area of one of the plates, because they're the same size, and that's going to be in meters squared. K is our Coulomb's constant, 8.99 times 10 to the ninth newtons meter squared per coulomb squared. D is the physical separation of the plates. That's in meters. Now, there's two different ways to think about this. You can either use the 4 pi kd in the denominator, or you can use epsilon sub 0 in the numerator. Epsilon sub 0 is the permittivity of free space, and k is actually defined by this permittivity of free space, which is fundamental constant. So k is actually 1 over 4 pi epsilon, which is why it looks like this. And so epsilon sub 0, also on your equation sheet, is just 8.85 times 10 to the negative 12th coulomb squared per Newton meter squared. Now, all electric fields store energy. So what we really want to do is be able to determine that the energy stored in a capacitor. So the electric potential energy between two parallel plates is just 1/2 the capacitance times the voltage across the plates squared. So, as an example, parallel plate capacitor has a separation of 110 microns or micrometers, and each plate has an area of 0.075 meters squared. There's a 12-volt potential difference applied to the capacitor. Determine the capacitance. Okay, so the capacitance is actually set by the physical dimensions. So I'm going to use the C equals epsilon sub 0 A over D. I'm going to plug in my epsilon sub 0, 8.85 times 10 to the negative 12th, my area in meters squared, 0.075, and the distance separating them, 110 micrometers, or 110 times 10 to the negative 6th meters. Punchy in our calculator, and we get 6.0340909 times 10 to the negative 9th, or 6.03 times 10 to the negative 9th farads. What's the amount of charge on one of those plates? Once we know the capacitance, finding the charge is relatively easy since we know the voltage, because capacitance is truly the ratio of Q to V naught, delta V. And so if we want to find the charge, we just multiply both sides by the voltage, and we take the capacitance that we just got times 12, which turns out to be 7.24 times 10 to the negative 8 coulombs, or 72 nanocoulombs, 72.4 nanocoulombs. And determine the energy stored in this parallel plate capacitor. Again, this is a straightforward calculation. It's just 1/2 the capacitance times the voltage squared. So 1/2 the capacitance we found in part A times 12 squared, and we get 4.344545 repeating times 10 to the negative 4th, or 4.34 times 10 to the negative 4th joules.